Hi everyone, we're Anna, Lauren, and Thomas, and today we'll be walking you through our project on SSL decryption of WordPress traffic using Wireshark and SSL keylogging. We will begin by introducing our project and how we set up our environment. The goal of our project was to demonstrate how encrypted web traffic over HTTPS can be captured and then decrypted using keylogging, specifically with the SSL keylog file method. We used a WordPress site as our test case since it mimics a real-world content management system that handles sensitive user information like logins, posts, and administrative data. First, we deployed a WordPress website and secured it using HTTPS. We did this by installing a valid SSL certificate, in our case using certbot and Let's Encrypt, so that the connection between the client browser and server was fully encrypted using TLS or transport layer security. Securing a site with HTTPS is essential for both privacy and trust. It encrypts data between the server and users, protects login pages, and improves SEO rankings. Let's Encrypt provides a free SSL certificate, and certbot makes the installation and renewal process simple. In order to retain the certificate, we connected the instance, installed Snapped, and installed certbot. From there, we connected the certificate to the domain name of the website, enabling HTTPS. Once the site was live and encrypted, we used Wireshark, a powerful network analysis tool, to capture traffic. The project involved two phases. First, capturing normal encrypted traffic without any decryption, and second, capturing the same traffic again, but with keylogging enabled, allowing us to decrypt the traffic and inspect the actual HTTP requests and responses inside the TLS tunnel. This allowed us to directly compare what a network analyst or potentially an attacker could and could not see in both scenarios. Next, we will explain how we enabled SSL key logging and configured Wireshark to decrypt the traffic. Modern web browsers like Chrome and Firefox support a feature called SSL keylog file, which allows them to write pre-master keys using the TLS handshake to a local file. These keys are critical because they allow Wireshark to decrypt the otherwise unreadable TLS session. To use this feature, we set an environment variable in the setting of the computer and named it SSL keylog file. Then we placed it in a folder. From there, we opened Wireshark, clicked on Edit, then Preferences, then Protocols, and finally TLS. There, we placed our keylog file under pre-master secret log file name. This caused the traffic to become decrypted. Here are the results of our packet captures and what we were able to see, both before and after decryption. Before decryption, there's a packet called application data repeated 3 times. After the SSL keylog file is applied, this packet is decrypted. The packet now reads as certificate, certificate verify, and finished. Certificate is the server's certificate for authentication. Certificate verify is proof that the server possesses the private key corresponding to the certificate. And finally, finished is a message to confirm the integrity of the handshake. This encryption of handshake messages protects sensitive information like certificates and reduces the risk of interception or manipulation during the handshake.
Continuing on, in our second capture, we found the difference in server hello HTTPS traffic before and after decryption. After we set up SSL key logging and decrypt the traffic in Wireshark, you can now see more details inside the server hello that weren't visible before. Before decryption, you can only see basic handshake operations. After decryption, you can see inside the encrypted parts of the handshake, such as certificates, session keys, extensions, and more. The TLS handshake server hello messages changes the application data protocol to handshake protocol after it's decrypted. Now for this slide, we're demonstrating how once you have an SSL certificate, the HTTPS traffic is decrypted in Wireshark, and you can then see the HTTP packets that come through, such as the GET or the admin or the login request. Normally, when a site uses HTTPS, all HTTP requests like get, page.html, or post login are encrypted inside of TLS. If you open a Wireshark capture without any special setup, you won't be able to see the HTTP methods, headers, or paths, just all encrypted application data. However, if you want to set up your browser to export session keys using something like an SSL keylog file, environment variable, you can decrypt HTTPS traffic in Wireshark. As a result, you'll be able to see the full HTTPS request made inside the encrypted session, including the method, the path, such as WP login, and headers, and sometimes even the body content of the post request. Even though the website uses a certificate and encrypts the data, if you have the session keys, you can still see clear HTTP traffic like normal. Without the session keys, everything stays encrypted. With the session keys, Wireshark can reconstruct and display the full HTTP request and response. Now for the TLS handshake, for the overview of the setup, the TLS handshake consists of the client hello, server hello, change cipher spec, encrypted extensions, certificate verify, and finished. These packets propose and confirm encryption parameters and are critical for setting up a secure channel.
Next, we're going to take a deep dive into the handshake. In the client hello, the client, usually a browser, tells the server what TLS versions and encryption methods it supports. It also sends a random value that will help generate encryption keys later. The server hello is the server's response. It picks the strongest encryption method they both support, sends its SSL certificate to prove its identity, and also provides its own random value. In the client hello, the browser proposes supported cipher suits and TLS versions. In the server hello, the server selects one and responds. This negotiation forms the foundation for the encrypted session that follows. For the server key exchange, here's what happens. After the client hello and server hello, both sides agree on a key exchange method. They each generate private values and exchange public information. Using a mathematical process, both sides independently calculate the same shared secret key without actually sending the key over the network. This shared key is then used to encrypt all the application data, protecting anything like passwords, web pages, and API requests. The server key is located in the server hello and completes the negotiation by sharing public key information necessary for creating the session key. The server's key exchange parameters are critical because they both help parties derive a shared secret key used to encrypt future communications. Without properly completing this key exchange, no secure encrypted session could be established. After this exchange and the final handshake messages, all data between the client and server is fully encrypted. In conclusion, this project demonstrated the strength of HTTPS encryption and also how it can be analyzed in controlled environment. Without access to encryption keys, TLS effectively hides sensitive data, but once those keys are available, such as through the SSL keylog file, we're able to see exactly what's happening inside a secure session. This technique is useful for developers debugging encrypted web traffic, for security analysts verifying behavior, and also a reminder of how important it is to keep key material secure. If an attacker ever gained access to those keys, they could completely decrypt private traffic, just like we did in our test environment. Thank you for listening. We're happy to answer any questions.